The limit of sine of theta over theta, as theta approaches 0, is 1 when theta is measured in radians. This fundamental limit plays a crucial role in calculus, especially in the derivatives of trigonometric functions. Observe that the input of the sine function exactly matches the denominator and approaches 0. The variable theta in the limit is a dummy variable, and can be replaced with any other symbol, without changing the value of the limit. Now, let's consider the limit of sine of f of x over f of x. Which number should x approach so that this limit equals 1? For this limit to be valid, f of x must approach 0. This means that x can approach any real number a, even infinity or negative infinity, as long as it makes f of x approach 0. Now, we discuss a useful generalization of this limit, where f of x, the input of the sine function, approaches 0, as x approaches a. However, the denominator, g of x, is not necessarily equal to the input of the sine function. To evaluate this limit, or to determine if it exists, we simply remove the sine function, leaving just its input, and work with the resulting simpler limit. Let's see why this generalized rule works in the most common case, when dividing by f of x is valid when we take the limit. We begin by multiplying both the numerator and denominator by f of x, and split the limit. As discussed earlier, the value of the first limit equals 1, which when multiplied with the second limit gives us the desired result. This shows that if f of x approaches 0 as x approaches a, the two limits will exhibit the same behavior. They either both exist and are equal, or neither one exists. Also, if one is infinity or negative infinity, so is the other. Using the reciprocal law of limits, we can also interchange the numerator and denominator in each limit. What if the function is not in the form discussed so far? Using the process discussed earlier, we can easily verify that each sine function factor in the numerator or denominator can be replaced by its input alone as long as the input approaches 0. The key point of our discussion is, in a limit where f of x approaches 0, the factors, sine of f of x and f of x, can be used interchangeably in the numerator or denominator. Now, let's find some limits using the generalized result. In this example, as x approaches 0, the input 6x of the sine function approaches 0. So we can simply remove the sine function, keeping just its input, and simplify. The value of this limit is 2. Next, we discuss an example where x approaches a number different from 0. In this example, as x approaches pi over 5, the input of the sine function approaches 0. So we can simply remove the sine function, keeping just its input, and simplify. The value of this limit is 1. Now, let's discuss an example where the limit will be infinity. In this example, as x approaches 0, the input of the sine function approaches 0. So we can simply remove the sine function, keeping just its input, and simplify. This limit is positive infinity. Next, we consider a limit in which sine functions appear in both the numerator and the denominator. As x approaches 0, the inputs of both the sine functions approach 0. So we can simply remove each sine function, keeping just its input, and simplify. The value of this limit is 0. Now, we discuss an example in which x approaches infinity. As x approaches infinity, the input 1 over x of the sine function approaches 0. So we can simply remove the sine function, keeping just its input, and simplify. The value of this limit is 1. Finally, we discuss an interesting example in which we apply the generalized result in the opposite direction. We apply sine to a function approaching 0. In this example, as x approaches 0, the numerator approaches 0. So we can apply sine function to the numerator, which gives us just x in the numerator. After simplifying, the value of this limit is 1.